All right, welcome to week 6. We are Tuesday, week 6. We're going to do section 7.1. Excuse my voice. It's actually coming back. It was pretty bad. This is a significant improvement. So I apologize. That was still pretty bad. Today's class is going to be really short. Normally we would do lab 4 after this section. And after I taught you this, I would show you lab 4, but because we're not doing lab 4 this term and we have a super short class, there's not even very much math involved. Sorry. It's really about definitions and just looking at things a little bit different way. We'll be doing all the math and learning fun calculator functions on Thursday. So we're only doing 7.1. After we're done, some people said they had questions about the homework. I can take questions about that and do a few problems as long as it's from 7.1 or earlier. I'll go through it. I'm not going to go through any 7.2 stuff yet because I don't want to confuse those who haven't seen it yet, who see the material first in this class. But I'll go through anything 7.1 or earlier. If you have questions of anything 7.2 or after, I can help you individually through messages or anything, or we can wait till Thursday. Sorry about that. All right, let's get going. Get the chat back up here. All right. So we're going to talk about different probability distributions, shapes of curves. We're going to talk about normal probability. I guess I should go back here. We're going to talk about the uniform probability distribution, talk about the graph of the normal curve, look at the properties of the normal curve, and then talk about the normal density function. So this is really a definition heavy section. 7.2 is where all the math is. And I think they're the same. I think they're in the same homework assignment, 7.1 and 7.2. I'm going to look real quick. I go back to my, so let's see here. Yeah, 7.1 and 7.2 are the same homework assignment. So it's a pretty actually easy week as far as math goes, except for next week you will have the test opens next week. Today you have the project proposal due. You can still propose a project idea after today, but you can only get the extra credit through today. Also, the hand-in homework, it is due tonight. I can answer questions and help you a little bit with that if you're stuck on that. And yeah, and we also have the quiz due tonight. Go back here. All right, let's do some talking. Sorry, once again, I sound terrible. Hopefully you can understand me. So a uniform probability distribution, it means that I just noticed that friend is typoed here. It says fiend. And it just kind of annoyed me. Sorry about that. Just distracted me. So the uniform probability distribution, when you graph it, it's basically just a rectangle. So a good example here is your friend could be on time from 0 to 30 minutes late. They have an equal probability of being any time late. They have the same probability of being 3 to 4 minutes late as he does to being 25 to 26 minutes late. It can take on any value, and it's equally likely to take on any value, kind of like rolling a dice. You're equally likely to land on any dice value. Getting a 1 has the same probability as getting a 3. So let's see here. As we were called before, the probability, a probability distribution, well, what happened? Darn it. Come on. I hate when that happens. All I did was move it onto my lap. Ugh. Okay. See if I can get this done quickly. If I can't get it quickly, then I will. See here. If I can't get it to fix quickly, then I will it'll be FaceTime. Be my face for a second. Let's try it again. If I can't get it to fix quickly, I'll pause. I'm going to pause the recording. Sorry about that, y'all. All right, now that I fixed that, sorry. So as before, before all of our probabilities had to add up to 1. When we're talking about a probability density function, the area under the curve of the graph, the total area, has to equal 1. Sorry. So the height of the graph everywhere across it is going to be greater than or equal to 0 for all of the values of x that the random variable can take on. So for like rolling a dice, for 1, 2, 3, 4, 5, 6, the area underneath that curve is going to be greater than 0 under each spot. I'll show you a graph of it. Here's the uniform density function. The entire area equals 1. Sorry. Since the probability is equal in each spot, and the thing has to equal 1, the whole thing has to equal 1. We've got 30 different values under here, or from 0 to 30. So he could be 2 minutes late, he could be 25 minutes late, he can be 15 minutes late, all the same probability. So each probability is 1/30th. Every single time, it's 1/30th of a probability. It's 1/30th of a chance being 1 minute late, 1/30th of a chance of being 29 minutes late. So the height of my rectangle is 1/30th, and the width of it is 30. The area under it, 1/30th times 30 equals 1. So that's the area under that graph is 1. So when we're using area as a probability, we're just basically, in this case, we'll create a nice rectangle for the area. We calculate the area of that rectangle. That will give us our probability. So let's take a look at A. What is the probability of your friend being between 10 and 20 minutes late? So this distance right here between 10 and 20 is 10, because there are 10 minutes between 10 and 20. Then the height here is 1/30th. So to find the area of that rectangle, I would multiply 10 times 1/30, and using my fraction multiplication, I end up with 10/30, which is 1/3. So there's a 1/3% chance, or about 33.3% chance of him being between 10 and 20 minutes late. So we can calculate probability as an area in this case. This is all going to come together really well pretty soon. So now let's take a look at this one. We know that the probability of him being late is 20%. We don't know how many minutes that is, but it's 10 a.m. So we're at 0. We're at 0. So we don't know this distance right here. But the area of a rectangle is width times height, or length times height. So I'm just going to use an x. So the x times 1/30th is going to equal 0.2, because the 0.2 is the 20% chance of being late. So I know x times 1/30, 1/30 equals 0.2. I'm going to math this out in order to calculate or get x by itself. It's not the color I want. I'm going to multiply both sides by 30, because 30 divided by 30 is 1. I'm going to use my handy dandy calculator. 30 divided by 0.2 gives me 150. What the heck? I did something wrong. Oh, times. I didn't tell me I didn't multiply. I divided. 0.2 times 30. I had a real big issue. Equals 6. So in this case, x equals 6. So there's a 20% chance that he will arrive in the next 6 minutes. Questions on this? All right, let's move on. All right. When we're talking about a bell-shaped curve or symmetric curve, it's also called a normal curve. We've been calling it bell-shaped or symmetric until now. It's also called a normal curve. And we're going to be pretty much calling it a normal curve from here on out. So when it has this nice bell-shaped, we call that normal. Sorry. I know that's really not attractive. Sorry. Okay. So this is a nice normal curve. Sometimes normal curves are wider, sometimes they're taller. When we get this bell-shaped, no matter what our belt looks like, this is called a normal curve. I'm not even going to worry about the inflection points. We're ignoring those for now. We're just going to ignore them completely. They're really helpful if you do calculus. Otherwise, we don't care about them. So if a continuous variable is normally distributed, it has a normal probability distribution, then our histogram is going to look like this. It's going to have this shape. Normally distributed. I'm still Slay. Thank you, Quentin. So if it has this nice, pretty shape, it's bell curved, it's normally distributed, and pretty much all of the math we do from here on out requires us to have a normal curve, requires our data to be normal. When it's normal, it's good. It means that we can do lots of things to analyze our data. So this would be the graph of a normal distribution. It's nice, it's pretty. There we go. Sometimes it's moved a little bit differently. It doesn't matter where it is on the graph or what our mean is or what our standard deviation is. As long as it has this shape, it's good. This is just different ways it could look. This blue one right here has a mean of 3 and a standard deviation of 1. This one is a mean of 0, standard deviation of 1. Take a look at this tall one right here. Still has the mean of 0 and the standard deviation of 1. It is super tall. This one has the larger standard deviation. It's more spread out, but it is still a nice, pretty bell curve. So all of these are nice and pretty, but we can still do our math with them. They're all normal. All right, here are the properties. So normal density curve is symmetric about the mean. The mean and the median and mode are all pretty close to equal to each other. They're really close. So it has one peak right at the center, right at our mean. It has that nice peak there. The area under that curve is 1. And the area to the right of it is 50%. And the area to the right of the mean is 50%. And to the left of the mean is 50%. So it's all nice and symmetric and beautiful. And I'm not going to ask you to recount these to me. I just need you to have them in your brain. I'm not going to ask you questions about this, like on a test or anything. I don't even believe I don't even think there's a quiz question about it. Okay. As we get larger and larger from both sides, as we get bigger and bigger to the right and bigger to the left, it's going to get really, really close to the x-axis, to the horizontal axis, but it'll never touch it. It's going to get really, really, really close, infinitely close. So the empirical rule for a normal curve applies, but it's not exact, it's approximately. So notice how we say 68% of the data is within 1 standard deviation. That's really an estimate. It's really close to the 68%. Same thing with the 95% within 2 standard deviations. It's not exactly 95%, but it is really close. I believe at 2 standard deviations, the z-score, or at 95% actually has a z-score of like 1.965. So it's really close to 2, but it's not exactly. So, but we just round it to that because it's easier. And statisticians don't deal in absolutes, as I've said before. Everything is approximate. Drives a lot of people crazy. We all know this picture. Seen it 100 times. Still applies. This nice bell-shaped curve. This is a normal curve. We use the empirical rule with a nice normal distribution. Put that down there. So these are all approximates, but you kind of get the picture. We've been here, done that, bought the t-shirt. I am like whipping through these. I told you it was fast. We're already on slide 11 and there's only 18. This is like the fastest lesson all term. And part of that's because lab 4 was a doozy. I don't like lab 4. I need to fix it. But lab 4 was a doozy and I don't like it. So you get a nice short lesson. All right. So on the next slide, our data represents the height of random sample of 52-year-old males, not 52, 52-year-old males. We're going to make a histogram and then we're going to talk about whether or not we're normally distributed. We're going to see what it looks like on a graph. I can like Google empirical rule and get that. I swear. You're going to make me have to check. I'm gonna Google it. I wonder if I can. I'm just curious. Okay, images. And there's a bunch of them. Did you Google empirical rule, Gwen? Yeah, they're there. I don't know how to make it simpler. I don't. I don't know other within the diagram. I wish I could figure that out, how to make it simpler for you. I'm so sorry you struggle with it. You're going to be using your calculator for a lot of it from now on. So hopefully we'll make it work. Okay. Here's all the data. Don't worry, you don't have to put it in your calculator. But this is 52-year-old males and their height. Here is my nice pretty graph. So I can draw this nice bell over top of it. It's a nice bell curve. So we have a nice pretty bell curve right over top of this. So clearly this is normally distributed. And it's never exact. It's never perfect. Almost never do we get a perfect bell curve. But we kind of play in the land of close enough. And if it looks close enough, we will call it normal. As long as it doesn't like look obviously skewed or you don't have super obvious outliers, we will just call it normally distributed. So once again, here's the curve over top of it. So we're going to talk about this slice of it right there. So it says, how does the area of the rectangle between 34.5 and 35.5 relate to the area under the curve? So if I cut off this little piece right here, so if I just cut off this little piece, I can take this and put it into here, and we're going to be really close to that area of that. Then I showed you in the normal or in the uniform distribution how the area fits the probability. If I took this right here, this 20% right there, and that's the height was 0.20, and multiplied it by this distance here by 1, there's about a 20% chance of getting a child, randomly choosing a child between 34.5 and 35.5. That's basically where our probabilities come from. So if you were like this calculus genius, which I don't expect anybody in this class to be a calculus genius, don't worry, you could actually take the integral of the curve between these two spots and you would get the probability, which is so cool. And if you ever take calculus, come back and see me or talk to me, and I will show you how to find probabilities using calculus. Don't worry, I don't expect anybody to know that, but it's super fun. Calculus is so much fun if you get the chance to take it. Okay, So suppose you have a random variable X. It's normally distributed with a mean of mu, standard deviation sigma. We have two different ways to interpret the area under the curve, depending on the question you're being asked. It is either the proportion of the population with the characteristics described, or it's the probability that a randomly selected individual will have those characteristics. So let's go back to the 2-year-old males. So I either have a 20% probability of choosing a random 2-year-old male and having them between 34.5 and 35.5 inches tall. Or I could say that the proportion of 2-year-old males that are between 34.5 and 35.5 inches is 20%. So those are the same thing. They're just stated different depending on what you're being asked. So I have an example. So the weights of giraffes are approximately normally distributed with a mean 2,200 pounds and a standard deviation of 200 pounds. We're going to draw a normal curve with this information. We're going to shade the curve for the left of 2,100 pounds. So we're going to take the 2,100 pounds and smaller. So we're going to look at the area of the curve under 2,100 pounds. So that area that we are shading, the area of that is 0.3085. We're going to talk about the two different interpretations. So here is my lovely shaded area. So 2,100 pounds is right there. It is shaded. So this area right here is 0.3085. So of the entire curve, it's about almost 31% of the entire curve. So the two different ways that we can interpret this area is we could say the proportion of giraffes whose weight is less than 2,100 pounds is about 0.3085, or that the probability of it randomly selecting a giraffe that weighs less than 21 pounds is 0.3085. So we can answer that question either way, depending on what they ask me. So about just under 31% of all giraffes are less than 2,100 pounds. Questions? See, this lesson took literally a half an hour. And that's the end. That's the end of my slides. The next one's empty, see? It is the end of my slides. So now I'm still on camera. So if you have recording, if you have questions on homework 6.1, 6.2, what are the homeworks that we had? Let's get rid of this. 6.1, 6.2, I know they're already passed. Or if you have questions on the hand and homework, or 7.1, which I'm not answering 7.2 questions yet. So using the calculator functions and things, I'm not answering those yet. I'll answer those on Thursday or one-on-one because I don't want to confuse anyone. So questions, I can go back and pull them up and, okay. Okay. So you're talking about, okay, let me. So the question, and I'm going to pull up the question, similar question in my open math. Which part is this? Where did you get this? Did you get that in 7.1? I'm not sure where you are. 6.2, okay. I'm going to find the similar question, Quentin, because I can't pull that up onto my screen for others to say. See, so let me take a look. Okay, I don't like that. No. This one right here, right? Okay. Okay. You really struggle remembering to bring your lunch to work. Each day seems to be independent as to whether you remember it or not. The chance you forgot your lunch each day is 28.4%. So are you looking for part B? Is that what you said? The last two parts. Okay. What would be either the first number of days larger than the mean that would be considered unusual? Okay. An unusual value is anything that occurs less than 5% of the time, right? Anything that occurs less than 5% of the time is considered unusual. So I'm going to open up my mean and my standard deviation right here, or anything more than 2 standard deviations away from the mean. I'm going to write them down. I'll write them down and I'm going to jump back. One second, let's write this down. Okay, I've got my mean and my standard deviation. I'm going to jump back to my other screen. So we want to know the last usual. So we want to know the first unusual value. I want to know the first unusual value. All right, so anything more than 2 standard deviations from the mean is unusual. So that's our 2 standard deviation rule. If it's more than 2 standard deviations away, it's unusual. So I'm just going to take my mean plus 2 times 2.852. Put that in my calculator. That is 17 plus 0.064. All right. So 17 days would not be unusual, because 17 days would be fewer than 2 standard deviations away from the mean, just barely, but it would be fewer. So the first day that would be unusual would be 18 days, because that's the first one past 2 standard deviations from the mean. Does that make sense? So this should be 18. Yes. Does that make sense? Okay. Now it says, find the probability of forgetting your lunch at least as many times as your answer to part B. So at every time you see at least. Okay. Every time you see at least, use the complement rule. Every time you see at least, use the complement rule. So I want to know the probability of forgetting my lunch at least, so that's greater than or equal to, at least 18 times. So I'm going to go back. I need to find my percent again, though. It was 0.284. All right. And I go back to the other screen. Come on, go back. Okay. So I have a probability of 0.284, and I need the probability at least, I forgot my lunch at least 18 times. So I need to know the probability of 1 minus the probability that X is less than or equal to 17. So I need to find out the probability I forgot my lunch 17 or fewer times, and then use that binom PDF or CDF. So it would be 1 minus binom CDF, the number of trials. I don't know. Uh-oh. Go back. I need to find my number of trials. Out of 40 days, 0.284, 17. So what this is going to tell me, I hate that. So what this tells me, this part right here, is the probability of forgetting my lunch 17 or fewer times. the 1 minus right here tells me, it takes those away, it subtracts those off, so that all I'm seeing is 18 or more. Yes, you do 1 minus every single time you see at least, you do 1 minus every time. So I'm going to put it in my calculator because I want to see if I get it right. I better get it right. All right. So it should be about 18.5%. Yeah. Or nope, 1.85. It says 1.85 on my calculator. The at most you don't have to do, but you don't have to do that because this one right here, this right here without the 1 minus, this would be the probability you forgot it at most 17 times. So it's 17 or fewer. So you wouldn't need the 1 minus because at most is less than or equal to. At least is greater than or equal to. That was given to me. The 0.284, it was given to me right here. That's my probability. Yeah. Are you okay, Quentin? I'm a little worried about you right now. You okay? Okay, good. Getting better. All right. Did anyone have any other questions on this assignment? Oh, toothaches are terrible. I had to have a root canal last year. It was awful. All right. Anyone have any other questions? The hand-in homework go well for y'all? Okay. Anyone have any other questions? I'm going to get off of the recording. I can figure out how to do that.